sufficiency theorem is it's kind of, it imposes pretty strong assumptions. Now, Arrow and Enthoven developed weaker conditions than the Kuhn-Tucker sufficiency theorem. And so we're going to call this second one the Arrow-Enthoven sufficiency theorem. And the Arrow-Enthoven sufficiency condition is this. Your objective function now is just going to be required to be quasi-concave. Quasi-concavity is a weaker condition than concavity. And we'll discuss quasi-concavity more in just a little bit. But so it assumes that your objective function in the non-negative orthon is quasi-concave. It assumes that each of these constraints is quasi-convex. Rather than convex, it assumes that they're quasi-convex, which is a weaker condition than convexity. Okay, so those are the major two changes. So you require that, and let's see, what else do you require? If you look at the book, that's A and B. C is the condition satisfies the Kuhn-Tucker maximum conditions. Okay, and then D, condition D will almost always be satisfied. So I'm not going to spend a lot of time on it. But D could be any one of four conditions that the partial derivative of your objective function at the optimal value x star, one of these partial derivatives is negative for at least one variable. Part two is one of them is positive for one of your x's, a positive value where you're not violating the constraints. Okay. And then three, the end derivatives are not all zero, and the function is twice differentiable. Or four, the function is concave. So almost always, condition two in economics, one of those partial derivatives, f sub j at x star is greater than 0. In economics, that'll almost always be satisfied. So what I'm saying is part D is for almost all problems in economics will be satisfied. So the two important ones you want to satisfy are that your objective function be quasi-concave and that each of the constraints be quasi-convex. Okay. And then you satisfy the Kuhn-Tucker conditions, and then you satisfy D, which is almost always satisfied. And look in the book for more details on that, and that'll guarantee a global maximum. Okay. Let's take our problem. Now, our problem that we did on the quiz today, let's look at our objective function. What was the objective function for the quiz problem today? Yes. Is this utility function quasi-concave? Okay, it's not concave. Okay, how do we know it's not concave? What would have to be true for this to be concave? Yeah, look at all these second derivatives. And let's follow the book's notation and think of u is utility is a function of x and y. So what's the easiest way to determine whether this is concave? Okay, well, we want to look at all the second derivatives. Let's get the derivatives. F sub x is 2xy. And we want to look in particular at the second derivatives. What is f sub xx? Yeah, that's just going to be 2y. F sub y is just x squared. F sub yy here is 0. F sub xy is equal to 2x. Now, how can you use those second derivatives to look at concavity? I know it's been a while since we talked about the conditions for concavity.
Isn't it the relationship between the square of f of xy and the product of fy and f of y and f of x?
Right. What we would want to show that this function is concave, first of all, what would we want about f sub xx? What would we want f sub xx to be to show that this is a concave function? F sub xx would have to be less than or equal to 0. Okay, you would have to have this. And you would also need f sub yy less than or equal to 0. And notice f sub yy is 0. Well, that part is satisfied. But f sub xx is equal to 2y. So right away, we know that this isn't concave. Not only would we need this, what else would we need? Think of the second order conditions. What are the second order conditions? For a maximum, f sub xx has to be less than or equal to 0. F sub yy has to be less than or equal to 0. And what else do you need for the second order? We need f sub xx times f sub yy to be greater than or equal to f sub xy squared. Okay. But if any one of these is violated, it's not a concave function. So right away, we see f sub xx, since y certainly can be positive, this condition is going to be violated for some values of y. Okay, so it's not concave. Okay, but is it quasi-concave? Well, let me just tell you the second order or the second derivative test for quasi-concavity. Any of you remember? What's the second derivative test? Well, it is this. And you need to reread this section in Chang where he talks about quasi-concavity. A sufficient condition for quasi-concavity is this. In fact, a sufficient condition. This is the easiest test, perhaps. For strict quasi-concavity, is this. Is the following. Take a minus f sub x squared. Multiply it times f sub yy plus 2 f sub x times f sub y times f sub xy minus f sub y squared times f sub xx. Okay. If that is greater than or equal to 0, then f is strictly quasi-concave. Okay. Now, let's see what we get when we substitute in. Again, what is f sub x? F sub x is what here? 2xy. F sub y is just x squared. F sub xx is 2y. Right. F sub yy is equal to 0. F sub xy is equal to 2x. So if we just plug into this formula here, what we get is the following. Minus f sub x. What was f sub x? It was 2xy. Square that. Multiply that times f sub yy. F sub yy is 0. Okay. Plus 2 f sub x, 2xy. F sub y, x squared. F sub xy was equal to 2x. Okay. Plus or minus, sorry, minus f sub y. So that's a minus x squared squared, okay, times f sub xx, 2y. We want this to be greater than 0. This term is 0. That drops out. We get a 2, 2, 2. That's 8. X, this is, oh, we got x squared, third, fourth, x to the fourth. And then we have a y. So this middle term is 8, x to the fourth times y. Minus, what do we have here? We have minus x to the fourth times 2, so it's minus 2x to the fourth times y. That is equal to 6x to the fourth times y. That is greater than 0. Notice x and y. We're assuming that those are greater than 0. So this is for all values of x and y greater than 0. This will be positive. So this utility function is strictly quasi-concave. Okay. The constraints, each of the constraint functions are linear. Both the income constraint and the calorie constraint, both of those functions are linear. A linear function is what? A linear function is both. Exactly, quasi-concave and quasi-convex. In fact, a linear function is both concave and convex. If the function's convex, it has to be quasi-convex, because quasi-convexity is a weaker condition. Okay. So you have the two main assumptions of the Arrow and Thoven sufficiency theorem satisfied. One, the objective function is quasi-concave. 2, each of the constraints is quasi-convex. We satisfied the Kuhn-Tucker conditions. And then part D, look at part D on 326. Just take part 2. One of the partial derivatives at the optimal value for x and y is positive. In fact, both of the partial derivatives are positive. So part 2 is definitely satisfied. So is part 3. None of the derivatives are 0. So part 3 and all the second derivatives exist. So both conditions 2 and 3 are satisfied. So all the assumptions of the Arrow and Thoven sufficiency theorem are satisfied. Okay. 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 The lectern doesn't have a very big lip. Okay. But let me, I sense that you don't have the understanding of quasi-concavity that I would like for you to have. So let me just go back and review this concept of quasi-concavity in a little more depth. And let me try to give you an intuitive understanding of quasi-concavity. A function is quasi-concave if all of its level curves have upper contour sets that are convex sets. So let's take this example here. I know that sounds kind of fancy, but let's take this right here. What are the level curves? The level curves for that objective function are just the indifference curves. And we know, we showed earlier, that each of these indifference curves for Ian have graphs that look like this. They're nice convex curves. First derivative is always negative. Second derivative is always positive. For example, if you look at the indifference curve for, say, u equals 100, it'll give you a nice graph that looks like that. What is the upper contour set? That's all the values of x and y that give you a utility of 100 or more. So the upper contour set would just be all the area to the right or above the indifference curve. So this would be the upper contour set. And you can see this upper contour set is a convex set. A convex set is a set where you connect any 2 points in the set with a straight line, and all the points along that straight line are also within the set. Okay, so give me any 2 points. Say this point right here and this point right here. These are points in the upper contour set. If you connect them with a straight line, notice all these points are also in the straight line. All these points along the straight line are also in the upper contour set. Or give me any 2 points. Say this point right here and this point right here. Both of these points are right on the indifference curve, but that's okay. All these points connecting these 2 points are also in the upper contour set. So as long as all the indifference curves are convex, then it means that utility function is quasi-concave. In this case, it looks like it's strictly quasi-concave. Okay. Okay. So, or let me go back and give an even more intuitive explanation of quasi-concavity. Let's take a simple case like this. This is the easiest to illustrate graphically. Suppose we have y is a function of a single variable x. Now x is just a single variable. A quasi-concave function perhaps would be a bell-shaped curve like this. It would have this property. If you take any 2 values, and again, this is right from the book. If you look at the discussion of quasi-concavity, in the book. That is in chapter 12. And let me see if I can find my notes. Yes, look on page 12, page 364. Actually, look on page 364. And I'm going to give you just verbatim from the book what the condition for quasi-concavity is in this case. Okay. F is actually this is on page 365, the algebraic definition. F is quasi-concave if and only if for any pair of distinct points U and V. Okay. So you pick any two distinct points, U and V, values of X, in other words. And we let theta be some number between 1 and 0. Okay. Be any value between 1 and 0. The following condition holds. For f of v greater than or equal to f of u, okay, let f of v be greater than or equal to f of u. That implies that f evaluated at theta u plus 1 minus theta v be greater than or equal to f of u. Okay, let me show you just what that means in the graph. Let's pick two values of x. Let's call one of them u and one of them v. Let's let this one be u, and let's let this be v. Okay. Then f of u is right here. F of v is up here. So this is satisfied. F of v is greater than or equal to f of u. Okay. Then for this function to be quasi-concave, it must be the case that the height of the function along the arc, the height of the arc, must be everywhere greater than or f of u. So this part right here, see, theta is any number between 0 and 1. So if theta is 1, you're right at this point right here. If theta is 0, you're right at this point.